The definition of a recursive function is a function that calls itself. Here's a PowerPoint chart that shows a very simple main program, and here's a call within the main program to calculate the factorial of the number 6. On the right, here's actually a little function that will do that. This is a recursive factorial function, and it has a long integer in fact is set to 1, and then it just has an if statement. So if the number that's passed in, so we have an input argument of number, if the number is equal to 1, then the function returns 1. If it isn't, if the number is 2 or larger, then the else part of the clause executes. And here is the main part of the calculation. In fact is equal to number times recursive factorial of number minus 1. So in red, you can see the call to the function itself. So we have the name of the function is up here, recursive factorial, and here we are calling the function within the function, the definition of recursion. Whenever you call this function, there's only one way out, really, and that is the number has to eventually get to 1. If it doesn't, then you would remain in this loop at the bottom and have actually an infinite recursion, and that's similar to an infinite loop. If we take an example, say 6, and we call the recursive factorial function with 6, then here's what would happen. Within the function, then the number is not equal to 1, so the else part executes. So the first part of this would be that number 6, or in factorial, would be 6 times the factorial of 5. Well, the factorial of 5 is not, if we call the function with 5, then 5 is not 1. So we would do the else clause, and we would have 5 times the factorial of 4. And this would continue until number reached 1. So one way that you could think about this is that each time you call the function, you get a new copy of the function with an argument that's 1 less. At the bottom, you can see a representation of what the calculation is doing. In the main program, we call N Factorial. We calculate N Factorial by calling a recursive factorial of 6. Okay, well, to do that calculation, we have to have 6 times the factorial of 5. So by the time we get to the end and we have number reduced all the way to 1, we have essentially made 6 copies, or we don't really make copies, but you could think of them as copies, with the last one being the factorial of 1. So when 1 is passed in to the recursive factorial function, then the return statement executes. So it returns the value of 1 to the previous copy, which was called with the number 2. That function can now complete. So the number 1 has been returned here. 2 would be the number for that copy. 2 times 1 is 2. That number then is passed back to the next previous copy of the recursive factorial call, that being 3. So we have 2 that's returned from here. The number is 3 for this copy. 2 times 3 is 6. Then we can return, in fact, from that copy to the previous copy, which was the recursive factorial of 4. Now you can see what happens, right? 4 then is multiplied by this previous multiplication. So 6 times 4 is 24. And the copy that was processing 4 now returns 24 to the copy that was processing 5. It calculates 5 times 24 to get 120. That's passed back to the first copy, which is factorial of 6. Now it can complete its calculation. So 6 times 120 is 720, and that is returned to the main program. So the recursive functions are sort of like a spring on a wind-up toy. When you call the recursive functions, they kind of wind themselves up until they finally reach a point when they start to unwind. And that's shown along the bottom here. As they unwind, it returns successive calculations to the previous copy until finally it's completely unwound and you have the final value going back to the main calling program. Here's another chart depicting the same thing. In this case, I'm showing one line of code from the main program, which is a call to the recursive factorial function. We send in 6. And in the rectangles below that, you can see the calls to the various copies of the recursive factorial function. Now, once again, I should say these aren't actually copies of the code. They're copies of calls to the code. So the main program passes in 6 to the recursive factorial. Then it passes the value 5 to a copy of recursive factorial. It passes the value 4 into another copy. That one passes the value 3 into another one. That one passes the value 2. And then finally, we pass in the value 1. And that will terminate the number of calls to the recursive factorial function. We have the if statement. Now, number is equal to 1, so the return process starts to take place. This chart shows the values that are returned. So if we look at the very bottom, we have N Factorial. It returns the value 1. So this last copy, this 6th copy of the factorial function returns 1 to the previous copy, which is processing to 2. So now the 2 times 1 can take place, the result being 2. That can be returned to the copy of the factorial function that was processing 3. Now 3 times 2, that gives us a value 6. So this copy is finished and it can return its result to the previous copy. So 6 goes back to the copy that was processing the value 4. Then its calculation can take place, giving us 24. That's passed back to the previous one. 5 times 24, that result is 120, so that's passed back to the first copy. And then finally, 6 times 120 gives us the final value, and that's passed back to the calling program. So there you can see how the returns take place, each returning its value for N Factorial back to the previous copy, and then finally back to the calling program. Now let's look at some actual code. In this program, I have already typed it in. It's a complete program, so you don't have to watch me type. We have the main program, and I'm going to use 3 different functions to compute N Factorial. The first one is just going to be an iterative function. It's just going to be a loop, and I'm just calling it factorial. Then I have 2 different recursive factorial functions. First one's just called rec_factorial, and that's the one you saw from the PowerPoint charts. And then finally, here's just a variation of that, which is a little bit shorter. Now, let's go look at these functions. The regular factorial function, all that does is to just use a nice little for loop that multiplies the numbers 1 up to n times each other, and then returning the value. So this is an iterative solution to N Factorial. And that one is not recursive. The next one is a recursive factorial function. It receives an argument, unsigned integer for number, and I've got some extra stuff here to do some formatting that you'll see how that works when we run the program, but it's not really, it's just output. It's not really part of the factorial process itself. The main part of the factorial process is this if statement. As with a loop, there must be some condition that will stop the recursion and begin to return and finally produce a result that's returned to the calling program. In this case, number has to reach 1 for us to terminate the recursion. If it is equal to 1, then I'm just printing out the value here. And you'll see the return statement with number 1 is shown right there. The interesting and the recursive part of this is for all numbers greater than 1, then the else clause will execute. So in here, we take the number that's passed in, and we multiply that by the factorial of the number that's 1 less than that. So with our example of 6, number would be 6, and then we call the factorial, recursive factorial with 5. And then as you saw previously, as long as we haven't reached 1, and this was pointed out on those PowerPoint charts, when we send in the value 5, then we will have 5 times the factorial of 4. And this will continue, and will continue to generate recursive calls until finally we hit the value 1. When that happens, we can return 1, and that returns from one particular copy of this factorial, this recursive function. Then the preceding one gets a value returned here. Then it can complete its multiplication times this number here and return a value of whatever it has. So the lowest one, recursive factorial 1, it returns 1 from here. Then the previous copy would be 2 times the value returned here, which is 1. So it can complete 2 times 1, and then it returns 2 to the preceding recursive call, which was 3. So then we have a 3 here times the 2 that was passed back here, and so on. So that's how you write these factorial functions. The last one I'll just go ahead and show you. This one I can shorten it up a little bit so that we don't even have to have the else clause. So this one's identical, except now we just have a simple one-liner. If the number is greater than 1, then we call the recursive copy of the rec factorial function, and that's all we need to do. If it's 1, then we set 1 up to in fact up here. So when the value 1 comes in, number greater than 1 would be false, so we just return 1. So this gives you exactly the same result, and it's an even shorter program than the function that we had right above it. Now let's go ahead and compile the program and give it a try. Okay, the program now is ready for me to type in a number. So I'll type in the number 6, since my example has 6. And the function is going to stop for each one of these cases. So the first thing that I'm doing is I'm just calling the iterative version of factorial. So that's not recursive, but that's the output. And that's what you see here. Calling iterative function factorial 6, and the value in factorial is 720. Then I'll hit the return key or any key, and we'll move on to the recursive call, the first version. So let me type here space. And now you can see what's happening. Each time we call the recursive function, then it will call itself. So we enter the recursive factorial with the number 6 there. Then if we look at the function, we'll see that, where am I? Number's not 1, so it calls another copy of itself with the value 5. So now you can see all of these calls. We enter with 6, we make a recursive call with n-1 or number -1, which is 5. It makes another call to 4 with the 4, then n-1, number -1 is 3, so we make another call, and then another call, and then finally we call the recursive factorial with 1. At that point, then we get the first return. Then the function kind of unwinds and it returns a series of values. So the 6th copy, the last one, returns 1. Then the 5th copy returns 2. Then the 4th copy, which is 2 times 3, gives us 6. And then we're almost back out. So the 2nd copy that we're calling is 6 times 4, so we get 24. And then this one with 5 times 24 is the 120. And then our original call, 6 times, or factorial 6, is 6 times that, which gives us 720. And that last copy returns to the main program with the number 720. So you can see I've kind of indented these and showing you the calls as you're winding up the functions, and then the return values that come when you're unwinding them. We'll see exactly the same result with this last copy. The results look exactly the same. And what I have done inside the code is I've got a little extra formatting in here that does the indentation so that you can see the kind of the cascading effect as you go down and then as you come back out again. So this is the classic example of the introduction to recursion using this factorial function. So it's pretty simple. The code's not very difficult to write, and in fact you can write a lot of programs using fewer lines of code if you do use recursion. But recursion is a different way of thinking, and sometimes it's kind of hard to get your mind wrapped around exactly how to write your algorithm if you're going to use this recursive technique. Well, that's sufficient now for the introduction to recursion using the factorial function, so we'll terminate this video here.